Today we're talking about Chapter 5, Section 4, Exponential and Logarithmic Equations. Now, the thing about exponential and logarithmic equations, and again, I feel like when I was taking this, I dreaded this particular portion because it's like, it's always something you kind of learn at the end, and then you just kind of, your knowledge just kind of disappears regarding it, okay? And I know I said this the entire semester, it's pretty easy, okay? And I guess what I call easy is we're not doing mindless computation. We're just moving things around. We're just going to go John Madden and just put arrows. Oh, let's see here. We're going to go John Madden and put arrows everywhere today. Okay, even though that second one was clearly not an arrow. All right, so here today, look at that. we have two objectives. All right, so objective 1. Let's see. Guess we'll go ahead and just snip this. Ain't nothing wrong with that. Alrighty, so in this section we learned how to solve exponential and logarithmic equations. The techniques and strategies learned in this section help us solve applied problems that are discussed in section 5.5. We start by developing a strategy to solve exponential equations. So objective 1, which is solve exponential equations. So let's see, we've already solved exponential equations using the method of relating the base. Okay, so relating the base, if you recall, is, if we have something like 3 raised to the x is equal to 3 raised to the x plus 3. That would actually never work. So let's actually do this. X squared minus 7. That might, I don't know. And then of course what we do is we equate the two exponents because my bases are the same. So we would just simply say x is equal to x squared minus 7, and then we would proceed, okay, to solve x. So that's what we do when we have the bases that being the same. Well, for example, we can solve this equation, which we did similarly, right, by relating the bases. But suppose we're given an exponential equation in which the bases cannot be related, such as 2 raised to the x plus 1 power is equal to 3. Okay, well, how in the world do we solve for that x if we can't relate the bases? All right, and of course, we're going to figure that out momentarily. And it's super duper easy. I'm telling you, it's really easy, guys. Let's see, does this help us at all? Not really, but we're going to proceed with this this thought process because I think it's important. Okay? So to find the x-intercept, okay, obviously what we're going to do is we're going to set f of x equals 0, which we do here. All right, and then we get to the 2 raised to x plus 3, x plus 1 is equal to 3. All right, we can't do the relating bases. Instead, we're going to have to recall what we've done before. All right, the logarithm property of equality. This is where we have, if we have the same log base. If we have the same log base, so log base b of u is equal to log base b of v, we equate u and b together. Right? And also we're going to have to recall the power rule. Right? If we have log base b of some u, what we do is we just take this r and we put it out in front. Okay? And of course that's what we get here. So those are two that we're going to be using today. Only 2 properties, and it's very easy. Very, very easy, I promise you. Okay. So we're going to use these 2 properties in example 1. Here we go. So now let's go ahead and solve it. Okay, so obviously we went over the point that we can't relate the bases to one another. Okay, instead what we're going to have to do is we're going to have to manipulate the equation. Okay, so you know how previously, if we add one to one side, we have to add one to the other side. If we multiply one side by 3, we have to multiply the other side by 3. So what we're going to do here, we're going to do something a little clever. Okay, so I can't get the flag on my 1 there, so that's just going to have to stick. Okay, that's going to be equal to, and let's put it 3. We're going to put it a little bit further out because I got to put something there. Okay, so instead what we're going to do is we're going to take the natural logs of both sides. Okay, so obviously we don't have the same bases, so we're just going to do, we're going to put an L in here, and we're going to put an L in here. Boom, right? We do what we do to one side, we do it to the other. Okay, and now we can proceed with our problem, right? Using the, I forgot what it was even called, the power rule for logarithms, right? Using the power rule for logarithms, we know we can put this x plus 1 out front. So let's go ahead and do that. Oh, and this is going to be a quick tip too. So we put the x plus 1 out front, so let's go and do that, x plus 1. And then what remains would be natural log of 2. Okay, now this is a pro tip, and I highly suggest you do this 100% of the time. Whatever you put out front, go ahead and put that in parentheses. The reason being is that if we do not have the parentheses there, then it would just look like x plus 1 natural log of 2. Okay, so make sure that whatever you put out front, you put that in parentheses. That way you know exactly what you're doing and you have your ducks in a row there, okay? And then, of course, natural log of 3 over here. Okay, well, I mean, that was it. That was the big move, right? Next, we're going to have to isolate that x. Okay, so in order to isolate that x, let's go ahead and use the distributive property here. And so, well, honestly, we can go about it either way, but let's go ahead and use the distributive property here. And so what we're going to do is we're going to distribute the x here, and then the 1 here. Okay, so this is going to give us x times the natural log of 2 plus 1 times the natural log of 2. And of course, 1 times anything is just going to be the anything, but I'll still write the 1 for right now to kind of show what we just did. Okay. Alrighty. So now what we're going to do is we're just going to subtract this from both sides. Okay, and again, 1 natural log of 2 is just simply natural log of 2, right? So this is going to now turn into x natural log of 2 is equal to the natural log of 3 minus the natural log of 2. Okay, and then the last step we're going to do is, of course, we need to isolate that x here. We need to isolate the x. So what we're going to do here is we're just going to divide both sides by natural log of 2. Okay, and let's go ahead and since we have that division, I'm going to go ahead and put this right up here. Okay, so we're going to the final solution is going to be x is equal to the natural log of 3 minus the natural log of 2 all over the natural log of 2. Okay, and that would be my solution. All right, real quickly though, before I do proceed, we cannot, and you better not, cancel that. Okay, we can only cancel factors. Factors being multiplication, right? This is that'd be the same thing as saying something like 9 minus 7 over 7, right? That's actually 2 sevenths, right? Because 9 minus 7 is 2. 2 over 7 is 2 sevenths, right? That'd be the same thing as saying this, right? And of course, 9 minus 7 divided by 7 is not equal to 9. Okay, so don't do that. Right? And that about sums it up. How many we got today? Ooh, we have 6 people. Right. So anyways, that's that. Let us proceed. Ooh, this one looks juicy. All right, so we're gonna. I think we should probably give this one its own page. Okay. Again, let's read it. So if the equation can be written in the form b raised to the u is equal to b raised to the v, then we solve u is equal to v. Easy peasy, right? If the equation cannot be written easily in that form, then we're gonna have to use the logarithm property. Okay, well that's easy. Right. I mean, we knew that, right? Thanks for that brain buster there. Right, here we go. This is definitely going to be at least a 2-pager because this first one looks like it's going to be fun to roll around in. Okay, not really, but okay. Here we go. Let me just shut up and we'll start. Okay, so A is 3 raised to the x minus 1 power, and that's going to be equal to 1 over 27 raised to the 2x plus 1 power. Okay, so here's the thing about this is you're going to have to be able to spot numbers that could have the same base. Okay, so here we're going to see the relationship between 3 and 27. We know that 3 and 27 are related in a way because if we take 3 and we cube it, then we get to 27. So let's go ahead and write that like this. Excuse me. I'm going to go 3 raised to the x minus 1 power. It's going to be equal to 1 over, we're just going to write this as 3 cubed raised to 2x plus 1 power. Alrighty. Well, what we're going to do now is we're going to take this 3 in the denominator. Oh my goodness. There we go. We're going to take this 3 in the denominator, and we're going to move it to the numerator. Okay, so we're going to rewrite that as the 3 in the numerator. So this now turns into 3 raised to the x minus 1 power is equal to 3 to the negative 3 power. Okay, does that make sense? Because obviously, if I'm moving a number from the denominator to the numerator, I take the exponent changes signs. Okay. Well, now this becomes So let's pull an arrow this way, saying we're continuing here. So we're going to say 3 to the x minus 1 still is on the left, and on the right, who would have thought that 1s would be my hardest number to write? And on the right, we know using our power rule, that we just basically multiply like this, right? Negative 3 times 2x, and then negative 3 times a positive 1. So this is going to turn into a 3 raised to the negative 6x minus 3. All right. Well, that's pretty easy now. Now we're in business. Now we have the same basis, so we can just proceed with what we've done before. So we can now say x minus 1 is equal to negative 6x minus 3. So if we just go ahead and add 6 to both sides, subtract 1 from both sides, and then divide by 7, it looks like we will have x is equal to a negative 7 halves. Okay, and that's it. That was A. So I mean, it wasn't as sticky as I thought it'd be, but a little bit of thought process there. And I'll be honest with you, B is easier. At least it's easier to me, and hopefully it will be to you once you see it. So let's go ahead and proceed there. I say B is going to be easier because there's no, okay, so how can I get this base to look like the other base? There's none of that. Instead, what we're going to do is we're just going to go ahead and write. We're going to we obviously have different bases. Let's go ahead and write it by taking the natural logs of both sides. So let's take the natural log of the left side. A natural log of 7 to the raised to the x plus 3. And that's going to be equal to the natural log of 4 raised to the 2 minus x. Okay, and then using our, I forget what it's called every freaking time, power rule for logarithms. Using my power rule for logarithms, again, I'm going to take the exponent and put it out front. Take the exponent and put it out front. Okay, so by doing that, this becomes x plus 3. Now again, make sure you put that in parentheses. And you know what? Actually, I'm not going to put it in parentheses, so I can just again show you what it would look like and show you the confusion, because this is a big deal. Okay, so if I wrote it like this, you would read it as x plus 3 natural log of 7 and 2 minus x natural log of 4. Those are completely different numbers. We don't want to do that. Okay, so instead what we're going to do is we're going to put them in parentheses, and now it's more in line with what we're looking for. It's x plus 3 times the quantity of natural log of 7, and 2 minus x, or it would be 2 minus x times the quantity of 2 minus x times natural log of 4. I might have said that first one wrong, but regardless, you see things, right? Half you don't listen to the words I'm saying anyways. So anyways, that's a joke. Actually, it probably isn't. Probably more than half. I lost my, oh yeah, now we're going to distribute, okay? So we're going to multiply the natural log of 7. Let's do a different color there for that. We're going to distribute here, here, and here, here. Okay, so we're going to distribute, and then this becomes x natural log of 7 plus 3 natural log of 7. It's going to be equal to 2 natural log of 4, and then minus x natural log of 4. Okay, so it's just the way it looks, right? So what do we need to do here? We need to isolate the two x's, right? So what we're going to do here is we're going to put the x's on one side. Okay, so we're going to put the x's on one side while simultaneously putting the two that do not have x's, which are these two, also on one side. Okay, so I'm going to go ahead and I'm going to add x natural log of 4 to both sides, because obviously this is a minus, so I'm going to have to add it to get rid of it. And then I'm going to simultaneously subtract 3 natural log of 7. Okay. So here we go. The left side now becomes x natural log of 7. And then I'm adding this to the left side because I want to have my x's over there, right? So it's going to be plus x natural log of 4. And it's going to be equal to 2 natural log of 4, and I'm going to subtract this from both sides, so it's going to be minus 3 natural log of 7. So again, I don't really know if I told you, I fully said why I'm going to be doing this. Again, it's because I need to have my x's on one side, right? If I'm solving for x, well then they must be on the same side. Okay, and by doing that, it makes it pretty clear that on this side, I have x natural log of 7 plus x natural log of 4. Okay, now natural log of 7 and natural log of 4, those are actual numbers. Okay? I don't know what they are off the top of my head, but those are actual numbers. Okay, but for a second, let's just use numbers 7 and 4. Okay, so if this left side said 7x plus 4x, right, is it not abundantly clear that I can factor an x out? 7 plus 4, right? So that's what I'm going to be doing. I'm going to be factoring an x out of both of those. So factoring x out, I have natural log of 7 plus the natural log of 4, 2 natural log of 4 minus 3 natural log of 7. Okay, so the last thing I need to do here, and I'm going to have to put this on a new page. Last thing I need to do now is I need to fully isolate that x. So I need to just divide both sides by this, natural log of 7 plus natural log of 4. So I will have x is equal to, my numerator over there is 2 natural log of 4 minus 3 natural log of 7 divided by the natural log of 7 plus the natural log of 4. Okay. And what is that number? Well, let's put it into our handy-dandy calculator, because it says for part B, round to 4 decimal places. So here we go, 4 decimal places. All right, so let's hope we don't screw this up. So I'm gonna put the numerator in parentheses. So it's going to be 2 natural log 4 minus 3 natural log 7. Going to be divided by the natural log of 7 plus the natural log of 4. Okay, so I've got 0.0, it's a negative 0, negative 0.91. And I guess the 4 decimal place would be 99, because this goes 9/8 when then the 5 rounds up. Okay, and so that's B. All right, in 1 second, I'm getting absolutely suffocated in here from my heater, so be right back. Oh. All right, let's move on to the next one. All right, so that was that. That was that. Even more examples. All right, so example 3, solve each equation round to 4 decimal places. All right, so this isn't too hard, right? So let's go ahead and start with A. we know we need to find a way to isolate that x, right? So, I mean, first things first, I can just divide both sides by 25, right? Divide both sides by 25, so I'll have e raised to x minus 5. That's going to be equal to 17 divided by 25. Okay. All right, now I'm going to take the natural log of both sides. So I'll have that's a horrible arrow. Let's do that one again. The natural log of e raised to the x minus 5. That's going to be equal to the natural log of 17 over 25. Okay. Next, we can, and we're going to this one time, okay? We're going to go ahead and put this x minus 5 in front of the natural log of e, which we're going to, we do it every time, but I'm going to go ahead and write it out, okay? And so hopefully you'll see what I'm doing here. So let's put that x minus 5 in front. So we have x minus 5 natural log of e is equal to the natural log of 17 over 25. Okay. Now, if you put into your calculator the natural log of e, well, those are they cancel out. All right, one's a logarithm, one's an exponent. They're both are involved in the number e, right? So they cancel out, so it just becomes 1. Okay, so this essentially, I'm gonna put it a little mark here and put a 1 there, just to really show. Okay, so then we get x minus 5 is equal to the natural log of 17 over 25. Okay, and then it's pretty easy here, right? We just add 5. So then we have x is equal to, and it still says 4 decimal places, so that's okay. So it says x is equal to, we had 5 to both sides, so we're just going to say 5 plus the natural log of, natural log is 9, top, the natural log of 17 over 25. Okay, and let's see what that is and as a decimal. 5 plus the natural log of 17 divided by 25. That is 4.61433. So 4.6143. Right, and that's A. Right, now let's do B. So this way. All right, so B. We have. Ooh, this is pretty good. Okay, so we have 2 like bases here on the left, right? They're both based E. Okay. Well, if we have like bases and the exponents, then what we do is we add exponents, right? Remember that? So if we have x to the 4th times x cubed, then we add the exponents. We have x to the 7th. Okay. So what we're going to do is add these exponents together. So we've got e to the, well, let's just write it out. So e to the, we've got 2x minus 1, and then plus x plus 4 is equal to 11. Okay. And then this becomes, looks like 3x plus 3, e to the 3x plus 3, e to the 3x plus 3, that is equal to 11. Excuse me. And we're going to take the natural log of both sides. Okay, and by taking the natural log of both sides, this is where I'm said I'm not going to go ahead. I'm not going to write this. I'm just going to go ahead and take the exponent down. Okay, so this becomes 3x plus 3 is equal to the natural log of 11. Okay, and again, I am taking the natural log of both sides. I'm just putting the 3x plus 3 out front, and I know the natural log of e is 1. Okay, so I'm just kind of cutting corners there. Okay. All right, well, solving for x, let's going to have to subtract 3 and then divide by 3. So this is going to become x is equal to the natural log of 11. I said subtract 3 and then divide by 3. Okay, and then that is going to be, oh man, we got the natural log of 11 minus 30 divided by 3. So we've got negative 0.2007. Okay. And that's example 3. All right. Okay, this is good. All right, so these are properties of logarithms that we've talked about before. Nothing new. They're just a refresher, right? We have a product rule where if we have the argument u times v, then we can split it up. The argument is u divided by v, we split it up, and of course we have our power rule, which we've been using consistently today. Okay, so this is just a recap, which is going to lead into some examples that I think is really nice because many students proceed into what I call the autopilot mode. Okay, and the reason why I call it autopilot mode is because I even do it as an instructor. I know I'm teaching a particular subject, I'm teaching a particular technique, and so, as either an instructor or a student, but especially a student, you just expect to be using that technique the rest of that section, right? And that's not necessarily the case, and this would be an example of it. So let's go ahead and begin this. What we're going to do here is it looks like we're just going to have to reverse this. We're going to put this 2 onto the x minus 1, right? Because we're just kind of reversing that power rule. So we're going to have, that's a log. First of all, it's a log, right? Log base 5 of x minus 1 squared. That's going to be equal to log base 5 of 64. Okay. Well, now, I guess this isn't really the autopilot problem that I thought it was, right? We'll get to it, but this should be pretty easy, right? We see that we have 2 logarithms and they are like bases. So all we have to do is equate the arguments with one another, right? So all we have to say is x minus 1 quantity squared is equal to 64. Excuse me. Okay. And then we can proceed here. Well, we take the square root of both sides, so that's going to be x minus 1 is equal to plus or minus 8. And then we're going to add 1 to both sides, so we're going to have x is equal to 1 plus or minus 8. So my two potential solutions are x is equal to, so 1 plus 8 is 9. And x is equal to 1 minus 8 is a negative 7. Okay, we're not done here though. Okay, so unlike the previous problems, we have to have a very specific number in my argument here. Okay, solve for x. Okay, and that number, my argument here, must be greater than 0. Not greater than or equal to 0, it must be strictly greater than 0. So we have to kind of check, okay? So if we plug in a 9 there, right, it's not so hard. 9 minus 1 is 8, so 9 is good. But negative 7 minus 1 is a negative 8, so negative 7 is not a solution. Okay? And again, we have to do that when we play with logarithms because the domain is very specific with logarithms. If you recall, let's see, we're going to do this. Exponential equations, we know that the domain is all real numbers, right? But logarithms are different. Their domains are from 0 to infinity. And of course, that's not the best drawing I've ever made. But we know that their domains are from 0 to infinity, not including 0. So that's very different there. So this reads, when a logarithmic equation cannot be written in the form of log base b of u is equal to log base b of v, as in example 4. Right? Example 4 is pretty easy. We adhere to the steps outlined as follows. And you know what? Similar to everything I've done this semester, we know that. All right. Again, that's just mainly for I don't know, just to kind of keep track of what you're doing. Instead, we're going to proceed because I know that examples work a lot better than words in most cases. And again, I don't, you know, maybe I shouldn't have been like that. We'll talk about this. Okay. And we'll go ahead and, you know, I mean, step number 1 actually is my last step that I even talk about. Okay. So that's why I don't even adhere to this at all. But I mean, obviously use properties of logarithms to combine logarithms of a single logarithm. If needed, we eliminate, we solve, and then we check for any extraneous. Okay. So realistically, these steps are steps that we know to do. So that's why I kind of fudged the line there a little bit and said, hey, we can go without it, right? But again, it's because we know the steps, but we have to isolate and solve, right? Okay, so here we go. Now we get to the autopilot part. Do we? Yeah, now we get to the autopilot part. At this point, since we've been, you know, taking natural logs of both sides, doing the power rule and things like that, you might have autopiloted your way into forgetting how to solve something like this. Okay, so let's go ahead and refresh our memories. So let's do this. We're going to do, how do I do this? All right, we'll do b raised to the y. It's going to be equal to x. Okay, that would be the same thing as log, that is a beautiful G. I don't remember how I wrote that one. Log base b of x is equal to y. Okay, so we have to remember this. The transition from logs to exponential and from exponential to logarithm. Okay, because looking at this particular problem, what we're going to do is we're going to transition it from this logarithm into its exponent, right? So then this particular problem becomes 4. Guys, that is a nice G there. Can't get over it. That is we have 4 squared, and that's going to be equal to 2x. I don't really have to write in parentheses actually. 2x minus 1. That's it. I mean, I say that's it, but now we can proceed. It's really easy, right? I mean, this is an 8th grade math problem, right? So this is essentially going to be 16 is equal to 2x minus 1. Let's just go ahead and add, well, yeah, it's not going to be pretty. We add 1 both sides and then divide by 2, so we're going to have x is equal to 17 divided by 2. 17 halves, okay? And now we have to see if 17 halves satisfies this logarithm, right? Well, 2 times 17 halves is 17. 17 minus 1 is 16, so this is good. This particular solution works out. Good job. And I actually won't keep that there. It might be misconstrued as something else. Like just a line. But anyways, that's it. Easy peasy, right? Hopefully. And as you saw there, let's see here. As you saw, I didn't really even care about that, right? I mean, I do, but I just did it at the end. If I wanted to determine the domain of the variable, if I followed along here, I would have done this. I would have said x minus 1. Let's put that in red. I would have said x minus, wait a second, is that the same problem? No. Here, I would have said 2x minus 1. All right, 2x minus 1, I know that's to be greater than 0. I solve for x, and then I would figure out my domain. Okay, and then I would have to make sure that this is within my domain. So the book isn't wrong. I just do it a little bit differently. Okay, and since you or somebody paid good tuition money to hear me speak, we do it my way. Here we go. All right, so let's just recall what we've done before. So it looks like we have two logs. It looks like they have the same base of 2. So if they have the same base of 2, what we can do, if you recall, so this addition sign means that we can multiply the arguments. Okay, so we're going to go and multiply the arguments out here. So we're going to do, can't replicate that G. We'll just have to stick with that. So we're going to have log base 2 of x plus 10 times x plus 6, and it's going to be equal to 5. Okay, so what we can do now is we can just simply say, okay, well this is easy. So we can write this in exponential form again. So we're going to say, do we have to? Yeah, 2 to the 5th is equal to my argument, which is x plus 10 x plus 6, okay? Which 2 to the 5th, 2 squared is 4, 2 cubed is 8, 2 to the 4th is 16, 2 cubed will be 32, so we got 32, that's going to be equal to, we're going to have to FOIL this, okay? FOIL it. So this becomes x squared, and then we've got a 6x and a 10x, which will be plus 16x, and then plus 60. Okay. All right, then it looks like we're going to subtract 32 from both sides. So I'm going to go ahead and put this on the left, because I like, no, I'm not going to put it on the left. I'll keep it on. Do this, never mind. So we're going to have 0 is equal to x squared plus 16x. Subtract 32, so I got plus 28. Okay, and can I factor this? I got 4, yeah, it's 14 and 2. It's pretty easy. So this looks like it can factor into 0 is equal to x plus 14 and x plus 2. Okay, so therefore my solutions are x is equal to, let's put that in green. X is equal to negative 14 and x is equal to a negative 2. Okay, well, now I have to plug these in. Let's plug in negative 14. Okay, negative 14 plus 10, that's a negative 4, so that tells me right away that's a no-go. Okay, so this is not a solution. Now let's plug in a negative 2. Negative 2 plus 10 is a positive 8, we're good. Negative 2 plus 6 is a positive 4, we're good. So x is equal to negative 2 is our only solution. Okay. So again, I have had students be like, okay, so they both can't be solutions because they're both negative. They're both negative, right? And that's not true. That's just not true. It's when you plug it in. It's when you plug it into your problem. If it's 0 or negative, then it doesn't work. If it's just negative by itself, it's okay. It can be negative. See, again, notice how negative 2 is a solution. All right, so let's move it on here. Yes. The original equation, because what we're doing all in the blue is solving for x. Okay. No. I see what you're asking. Good question, and I totally forgot about it, so I'll be using that thought process in the future. All I'm caring about is the domain, okay? Because what happens here is I'm solving for x, the x values, okay? And we're equating it down here to 0 because of our zero-product principle, okay? That we learned many months ago. All right, and so once we did that, we got our x values that solve for x in my equation. Okay, but here's the thing: once I get my x values, they must be in the domain of my equation. So similar to problems that we've seen before. Let's see here. We might have had problems like this. 3 plus, no, let's just put it there. 3 over x minus 9, okay, is equal to 0, right? For this particular problem, we know that 9 is not in the domain, right? So if I put a 9 in there, then 9 minus 9 is 0, and we can't have a 0 in the denominator, right? It's not in the domain of this function. Okay. Similarly, that's what we're doing here. We're solving for x, okay, but then we have to make sure and check that the x value works in the domain of my logarithm. Yes, that's all you're looking at. You're just looking at right here. You're plugging it into those. Because I mean, if you plug in negative 14 and negative 2, they will make this entire thing true, right? Well, actually, no, it won't. I take that back. No, never mind. It won't make it true because we won't get past the part where it won't work here. If I plugged in negative 14, so if you plugged in, log of negative 4, you're going to run into an error on your calculator because correct because if you're whatever you plug into your logarithm, whatever the argument is of your logarithm, I think I erased it, so I just have to draw it again. Okay, if you recall your logarithmic equation, when you graph it, looks something like this, right? And so the domain of that, right? The domain, the only x values I'm allowed to use are all the x values that are greater than 0. Right? I mean, if I were just to ask you, hey, so what's the domain of that red line there? You would say, well, it looks like it's 0 to infinity, right? And that is the domain of the logarithm. It's 0 to infinity. So I can only use values that are positive. It's 0 to infinity and not including zeros with. So they must be positive. Log of 0 is like dividing by 0. We cannot do that. Correct. Right? No, you're good. And if you are, I'm sure somebody else is. So again, let me just recap this. If I were to plug in negative 14 into here, negative 14 plus 10 is negative 4. You cannot take the log of a negative 4. Okay? But if we plug in a negative 2, negative 2 plus 10 is a positive 8. That's good. We want that. We want it to be positive. Right? And then if we plugged in a negative 2 here, negative 2 plus 6, well, that's a positive 4, which is also positive. So that's why negative 2 works. That's why the number negative 2 works. Because when I plug it in, it still makes the argument a positive number. Make sense? And to expand more on that, let's look at this up here. Okay. All right. So the reason why this number must be greater than 0. Okay. Well, let's just assume. Let's just play with the fact that maybe it is 0, right? So let's just play with that fact. Log of let's say 3, and then put a 0 there is equal to some y. So if I wrote this in exponential form, 3 raised to the y power is equal to 0. Well, you cannot raise any number to get to 0. That's why that argument must be a positive number. So anyways, good question. Thank you. I will remember to clarify that in my future lectures. Alrighty, so solve natural log of x minus 4 minus natural log of x minus 5 is equal to 2. Oh, do we round? No, we didn't have to round. Okay. So this is we see that we have a subtraction sign here, so we can just go ahead and make this a division, right? So we can say the natural log of x minus 4 divided by x minus 5, that's equal to 2. Okay. Well, excuse me. If you recall, make that end a little better. If you recall, the natural log, still same looking at, the natural log is basically, so the natural log is basically log e. Okay, it's just the base being e, 2.71828. It's so prevalent in mathematics that we just use it, that it gets its own notation, ln. Okay, so if you think about it like this, we could essentially think about it written like this. Log of e, x minus 4, x minus 5 equals 2. Okay, so it's essentially written like that. And therefore, hopefully, now it's abundantly clear that if I were to do the logarithm rule here, like changing from log to exponents, then we'd say e raised to the 2 is equal to my argument, which is x minus 4 over x minus 5. Okay, and of course we can make that jump here as well. All right, anyway, so e squared is equal to that. Okay, so this is pretty good. So we're trying to solve for x. So, and we have the x's on one side, that's good, but they're being divided by one another. So how do we work this, right? So we're gonna do some fancy math here. Not too fancy, but we need to get the x and isolate it by itself. Okay, so what we're gonna do here is we're gonna go ahead and clear the fraction. Okay, so we're gonna multiply both sides by x minus 5. So this becomes e squared times x minus 5, x minus 4. Okay, and then we're going to distribute the e squared on the left side. So we're going to have e squared. Sorry, we're probably right. Well, no, that's good. E squared times x minus 5e squared is equal to x minus 4. And so now it should be clear what we're trying to do. Again, we need to isolate the x's. So this is very similar to what we did. One of these problems we did it. I don't know. But it's very similar to a problem that we did earlier, where we had to isolate the x's. So I'm going to have to move this x to this side, and I'm going to factor it out, and then I'm going to go ahead and move this 5e squared to the right side. Okay, so this becomes e squared, let's put an arrow there as a continuation, e squared x, and that's going to be minus x, okay, because we're subtracting x from both sides. This is going over here, and that's going to be equal to 4 plus 5e squared. Okay, what was that? I know I probably... This one, yeah, okay, so I should have went back one more. Okay, so remember, if you recall, what I did here was I put the two x terms on one side. That way I can factor an x out, okay? So I'm essentially doing the same thing here. I'm putting the x terms on one side so I can factor the x out. Okay, so let's proceed with that. So this turns into x is factored out, and I've got e squared minus x minus 1, and this is going to be equal to 4 plus 5e squared. Okay, negative 4. Yeah, it should be negative 4. Yeah, so let's go ahead and fix that up. Thank you. So we got... Where am I at? Oh yeah, I was factoring it out. And then I've got x minus 4 over here. Sorry about that. Okay, so then we can proceed. We're going to factor the x out. I guess I don't have to erase everything, huh? E squared minus 1 is equal to x minus 4. And this is definitely one we're going to have to put onto the next page. So we can go down here. Now we're going to divide both sides by e squared minus 1. So we're going to have x is equal to x minus 4 divided by e squared minus 1. Wait a second. I'm missing a lot. Hang on a second. I needed to... Oh, gosh. No, I did. I went absolutely stupid here. I can't erase that. Oh, okay. Well, that's good. Yeah, sorry about that. So first of all, do you guys remember that autopilot thing I was telling you about? We're here, okay? Yeah, so I completely autopiloted. Yeah, well, obviously, the mistake I'm making here is I wanted to isolate, excuse me, I wanted to isolate our x's here, and I was completely rewriting this instead of pulling the x over there. So yeah, that was my bad. So let's go ahead and fix that up real quick. So again, the left side, e squared x, and then it's a minus x over here, and then it's going to be equal to a 5e squared minus 4. Whew, okay, now we can do this. Right, and just so we're clear, I'm going to go ahead and keep that flub in this video, because I feel like it really goes along with the autopilot thing that I was speaking of earlier. That way everybody that ever takes my class again and watches this video will know. Okay, so we've got e times that, right? So by isolating the x, we need to divide both sides by e squared minus 1. So we're going to have x is equal to, and this is just going to be fun to put into the calculator. There we go. And so is this a 4 decimal place? Yeah. E squared minus 4 divided by e squared minus 1. That's 5.1565. 1565. And that's it. That was painful. Sorry about that. 5.1565. I mean, oh, well, we're done. I mean, yeah, that's the thing is, I mean, I'm not impervious to mistakes, even though I've been doing this for many, many years. But that's the way it is. I'm not ashamed of it. So, anyways, that does conclude today's lecture.